Hey guys, in this video, we're going to do a few more examples where we use an appropriate change of variables or change of coordinates to compute a double integral. So at this point, you might be asking yourself, like, why is this a useful technique? For example, the previous video, we computed that the area of a circle is pi r squared, and it took a lot of work to get to that point, and we already know the geometry formula pi r squared. But the reality here is we learned a technique that's going to be very versatile and applied to a lot of other situations. So there's a lot of problems where pi r squared is not going to do the trick for us because we're not doing an area calculation. If you take your double integral and you add a function f of xy as your integrand, then suddenly pi r squared is not going to do the trick anymore. And so we need another technique. Now, we did learn the Gauss-Green formula in a previous chapter. That would also work for us. But there are some things about a change of variables that is just a really slick way to approach a lot of these problems. All right, so we have example number 1 here, where we're going to compute this double integral of x squared plus y squared dA over the region satisfying these three inequalities. And these three inequalities give us this half donut shape here on the xy plane. It's basically the area that's between a circle of radius 5 centered at the origin, a circle of radius 2 centered at the origin, and above the horizontal line y equals 0. Now, remember, this is not an area calculation, so I can compute the area of this half donut pretty easily, just doing pi r squared over 2 for the big circle minus pi r squared over 2 for the small circle, but that's not what we're asked for, right? We're not supposed to compute the double integral of 1 dA. Instead, we want the double integral of x squared plus y squared dA. And so we have an integrand here that's not equal to 1, which means that we could imagine this as a volume calculation where we're getting the volume between the paraboloid x squared plus y squared and this base on the xy plane. I can't draw a perfect rendition of it by any means, but it looks somewhat like a Roman amphitheater of some sort, because what you have is this donut shape sitting on the xy plane, and then the surface is kind of rising up and away at all points, something like that. So you can almost imagine having like a seating gallery like this, and then, yeah, it's just not a great picture, but yeah, kind of imagine a football stadium or an amphitheater of some sort where we have our seats up here and everybody's kind of looking down from this gallery at, a football field or a stage or something like that. All right, so let's see how to do this computation in a clever manner, right? We don't really want to do this in xy space because it would not be a particularly nice integral to set up. If you wanted to compute this as a dy dx integral, we would have to break it up into a set of 3 distinct double integrals because our top curve and our bottom curve keep changing, right? We've got the big circle and then a horizontal line on the x-axis, then the big circle and the little circle, so on and so forth. There's going to be a lot of square roots in it. That's not really something that you want to try to do using xy space. So instead, we want to adopt a clever change of coordinates. And in this case, polar coordinates are going to do the trick. Because, I mean, look at everything in the problem. It's all based on circles, right? Circle of radius 5, circle of radius 4, and even this integrand has x squared plus y squared in it. So even that integrand we can make a lot simpler. All right, so I know that this thing doesn't look like a rectangle to you, but this is the weirdest looking rectangle you've ever seen in your life, because if we map this over to RT space, it really is a rectangle because t goes from 0 to pi. So our angle t rotates from 0 to pi, and r varies from 2 to 5. So this is an RT rectangle. So we can do our change of coordinates here. Now, you could look at my limits of integration. R goes from 2 to 5, t from 0 to pi. And then how am I setting up the rest of this integral? Well, I have my x squared plus y squared, my original integrand. I'm just going to substitute x equals r cosine t and y equals r sine t in for every instance of x and y in my integrand, and that'll kind of take care of it. So here, let me clean up this expression, or clean up this slide a little bit so there's not so much going on here. And really all I'm doing is I'm replacing x with r cosine t, y with r sine t, and then I'm evaluating x squared plus y squared, or r cosine t squared plus r sine t squared. Now there is one more piece of it that's important. When you do this change of coordinates, you have to use your Jacobian determinant. You have to use your area conversion factor, and that's what you see appearing right here. This factor of r is what adjusts for the fact that we're mapping to a new coordinate space where the mapping is not area preserving. So this is our adjustment factor that adjusts for area in our new coordinate space. All right, so now let's start cleaning this up a little bit. We have the Pythagorean identity here. If we have cosine squared plus sine squared, that equals 1. So this entire parenthetical here, this expression reduces to r squared. R squared times r is going to equal r to the third. Now there is a trick that will get us to r cubed a little bit faster. You could go straight to r squared if you realize when you're mapping between rectangular coordinates and polar coordinates, we know that x squared plus y squared is equal to r squared. So we can go directly to putting r squared in there. But if you want to just plug in x equals r cosine t and y equals r sine t, that gets us to the same place in the end. So either one works for me because you're going to get your answer either way. All right, the rest of this is integrating over a rectangle. So we have a fairly simple integrand, and our limits of integration now are constants, which is nice. So this double integral becomes pretty easy to sort out. We get 609 pi over 4. And remember, that is not the area of our half donut, but rather the volume of the kind of Roman amphitheater or stadium or whatever that's described by this surface, x squared plus y squared, floating over that half donut shape. Guys, what I did on this slide was just kind of, I tried to show you that mapping between RT space and XY space. So you can kind of see how we have a rectangle that's living in RT space, and then when I drag the slider, it maps it over to XY space. So I wasn't kidding. This half donut is the weirdest looking rectangle you've ever seen in your life. It's half an annulus if you want to be really technical about the name. It's not really a half a donut, but it's half of an annulus instead. All right, guys, so I know that everything I've done up until this point was with polar coordinates. This entire change of variables, change of coordinates technique really applies to a lot of different mappings between coordinate spaces. So a lot of different change of variables scenarios. It doesn't have to be polar coordinates. So in general, you can just take the formula from the previous video and replace all instances of r and t with u and v. That's typically what you'll see in a textbook for change of coordinates, change of variables. And really, everything we do from here on out should remind you of something that you've seen in a previous calculus course. Basically, U substitution, right? You did this in a single variable calculus course, in your Calc BC course, U sub. Now it kind of looks like UV sub, but it's the same idea at its core. And you guys saw this happen. So, let's say in your single variable calculus course, you want to compute an integral of f of x dx. And then you realize like, oh, this problem would be way easier if instead of working with x, instead I had a substitution here where x gets replaced with some x of u, some function of u, just because it makes your integration easier for some reason, right? Depending on what the nature of that substitution is. Now, did we have an area conversion factor when we changed our function to a function of u and we integrated with respect to u? You bet we did. So we thought of it as chain rule, but it's doing the same work, which is adjusting for the fact that the rate at which x changes is different than the rate at which u changes, right? You can't just arbitrarily change a variable in an integral without accounting for the effect that that would have. Right here, you could see that I wrote x prime of u du, but if you think of that more in a chain rule way of looking at it, that's going to be dx du du. So what we're accounting for is the rate at which x changes with respect to a change in u. And so that we do have our version of an area conversion factor in a single variable calculus course. So long story short, you could think of the Jacobian determinant, the area conversion factor, as kind of a higher dimensional analog of u sub, right? You did this with u substitution. I could try a quick example. I'm going to go through it pretty quickly because I don't want to extend this video more than necessary, but let's look at an example that might be reminiscent of something that you did in your Calc BC course. All right, so I have an integral here in a single variable that I want to compute the integral of the natural log of x over x dx, and then I've got I'm integrating from e squared to e to the sixth. All right, so let's remember this formula from the previous slide. Don't worry, I'm not testing you on this. So I know this is going to be a little bit different than you did u sub in your previous course, but at its core, it's going to be the same. So if my function is natural log of x over x, I could say, you know what, I'm going to replace all instances of x with e to the u. And by the way, that means that x prime of u is also equal to e to the u. So I could plug that all into this formula that I have up here. So, okay, I'm going to have f of x of u, x prime of u du. So I'm going to plug in, remember for all instances of x here, I put in an e to the u, also an e to the u for x prime of u, and then I've got a du. Plug e to the u into my function, my natural log of x over x, I get u over e to the u times e to the u du, get a little bit of cancellation there, and now I have the integral from 2 to 6 of u du. Now, do I have to be a little bit careful about how I do this? Yeah, like for example, look at how my limits of integration used to be in terms of x, and then I changed them over to u's. So keep that in mind. But at the end of the day, I compute my integral here in terms of u, and I get 16. Now, you might have seen this kind of backwards in your, it's not backwards, just from a different perspective in your Calc BC course. You probably wouldn't have written x of u equals e to the u. You would have done this in the more familiar form. You would have said u equals natural log of x. Well, if u is equal to the natural log of x, that means that x is equal to e to the u. Those are inverse statements of each other, so those both work. And then you would have said that du equals 1 over x dx. Well, you get the same result from that. You still get the same setup that you see right here, and you still get the same answer of 16. All right, so long story short, what we're doing in this chapter is just the multivariable analog of u substitution that you saw in your previous calculus course. All right, so let's move beyond polar coordinates here. So in this case, I don't have a circular region. Instead, I have an elliptical region. Now, what you guys are going to start to find out is that if you can parameterize it, you could probably integrate over it. This is not a guarantee, but this is a general guideline to try. If you can parameterize a region, you could probably integrate over it. Because you guys saw this over the previous examples, if you could parameterize a curve, that's really, if you could parameterize a region, that's a mapping between a UV rectangle and in this case, an XY ellipse. So if I could parameterize the ellipse, I can integrate over it. All right, so I know how to parameterize that ellipse. I have x equals 2u cosine v and y equals u sine v, where I'm going to let v vary from 0 to 2 pi, and u is going to vary from 0 to 1. That'll fill in my ellipse, which is the region that I want to integrate over. All right, so I don't have polar coordinates, so I can't just use the Jacobian determinant from polar. I can't just use the area conversion factor from polar. I actually got to compute this. So here is the formula as a 2 by 2 determinant. And we do have some partial derivatives to compute, but none of these are that big of a deal, and they're also very similar to what you saw in the previous video. So if x is equal to 2u cosine v, I need to compute dx du and dx dv. I'll get 2 cosine v and negative 2u sine v. And then in a very similar fashion, I also need to compute, if y is equal to u sine v, I need to compute dy du and dy dv. So those partial derivatives are the derivative of u sine v with respect to u is sine v, and the derivative of u sine v with respect to v is u cosine v. All right, so now I have a 2x2 determinant that I need to compute. Here it is. And then we have a little Pythagorean identity there. So let's simplify, and we get 2u. Guys, one thing to notice, by the way, there is a cool pattern here in this 2x2 determinant that we're computing. Look at the first row of this 2x2 determinant. That looks like the gradient of x with respect to uv, the gradient of x if we treat x as a function of uv, right? Basically, x equals 2u cosine v. That is treating x as a function of u and v. If you compute its gradient, that's the first row of our Jacobian matrix. Same thing for y here. If we treat y as a function of u and v, then the gradient of y is the second row of this 2x2 Jacobian matrix. So in general, you don't necessarily have to memorize all of the derivatives that appear in this 2x2 determinant here. Instead, you can remember how to come up with the matrix and then take its determinant just by remembering that you have a row of the gradient of x and a row with the gradient of y, and then you compute your determinant from there. You guys will see this come up throughout the courseware, and so you'll see it come up in the basics and tutorials. You might have to explain it every once in a while in a try-it problem, so just keep in mind that you should look out for that pattern as you're trying to remember this formula for the area conversion factor. All right, so now I want to finish my computation here. So here's the integral I wanted to compute. Notice it is not an area calculation because I do have an integrand. In this case, my integrand is y squared. So we're imagining that we have some surface floating above our ellipse, and we're computing the volume that's trapped between that surface and the ellipse. Technically speaking, it's volume above minus volume below, but in this case, similar to the previous example, we have a surface that is always above, on or above the xy plane, so we don't really need to worry so much about volume above minus volume below. Anyway, let's try out our change of variables here. So I know that I have x equals 2u cosine v and y equals u sine v, so I'm just going to replace all instances of x and y with those formulas. So I just need y squared here. So u sine v squared is u squared sine squared v. And then I do need my Jacobian determinant, so that's my area conversion factor. Now, technically speaking, it has absolute value bars on it, but since u is only going from 0 to 1, 2u will always be positive as u goes from 0 to 1, so we don't have to worry about absolute value bars there. And then the rest of this is a double integral that I think you guys would be pretty good at computing. So if you want to pause the video and try to compute it yourself, that's not a bad idea. It's some good practice. But let me bring you through the calculation until finally we get to an answer of pi over 2. And that is the value of the double integral of y squared dA integrated over that elliptical region. And what's kind of cool is we did a computation in UV space, but it gave us a result that describes something we're interested in XY space. All right, guys, finally, I mentioned this in both videos so far, but I'm going to keep coming back to this, which is one idea that I want you to take away from this chapter is that a parameterization of a region in XY space is actually a map between a UV rectangle and your XY region. And so the long story short is if you can parameterize a region, you could probably integrate over it. No guarantees, there's some exceptions here, but in general, if you could parameterize a region, you can expect that you can probably integrate over it. And the other thing that you can see is, I brought this up before as well, but I was really picky in earlier chapters about putting down your bounds for your parameterization. If you're parameterizing a region, you should say what your parameters vary between. And the reason I was picky about that was because I knew that these bounds for our parameterization become our limits of integration when we start setting up double integrals. Anyway, guys, thanks for tuning in. We've got one more video in this series. I'm just going to compute a few more interesting examples.